In school, you may have learnt about how waves on the coast were caused by friction of the water body against the seabed, causing the wave to slow down and collapse on its own weight, or how the prevailing wind causes disturbances in sea level, resulting in the small waves we see on a lovely beach holiday. But what about waves further from the coast? Instead, we look at the rise of such gravity waves on Earth and how coastal waves are a result of some very important fluid mechanics. Let us take a mathematical approach to construct models for waves on Earth. Firstly, shallow wave equations form some significant underlying physics. Momentum equations of a non-rotating fluid are as follows, specifically for the xy plane, i.e. in the horizontal direction. If we take the assumption that the fluid is of sufficiently shallow depth, hydrostatic equilibrium can be observed. We arrive at the mass conservation equations through simple substitution of this nabla operator with the velocity vector, remembering that we only observe the horizontal direction x and y, hence there is no w component of the velocity. Performing the space derivative of the momentum equations at the top and the time derivative of the mass conservation equations, we end up with the characteristic wave equation. Note that for this mathematical approach, two very important assumptions have been made. That the horizontal length scale was much larger than the vertical length scale, and we have very small vertical velocities. The next step is determining physical solutions to wave equations. Such waves are affected by gravity and Earth's rotation, resulting in a Coriolis effect. As a result, the shallow wave equations must be adjusted to accommodate for this Coriolis acceleration. Performing the space derivative of these new momentum equations and the time derivative of the same mass conservation equations as before, we arrive at a new equation where zeta is now equal to the relative vorticity of the fluid. Solutions of this wave equation are termed Poincare waves, and these have very important geophysical implications. Such implications are Kelvin waves. Taking a cross-section of a coastline and defining our axes x, y for horizontal motion, we can observe a specific fluid parcel. We have a velocity acting in the positive x direction, a horizontal pressure gradient force acting away from the coast, and a Coriolis acceleration acting towards the coast. As pressure gradient force equals Coriolis force, we have geostropic balance. This horizontal pressure gradient force arises from the uneven elevation of the sea surface towards the coast. Important points to be made are that in the northern hemisphere, Kelvin waves travel with the coast to their right and to the left in the southern hemisphere. Kelvin waves are a special case of Poincare waves whereby no motion occurs in one direction. Remembering our momentum equations, in this case v equals 0, resulting in these terms no longer contributing, as we have assumed that no motion occurs in the y direction. This gives us mass conservation equation, and recalling that our gradient operator only returns the x component, as we have taken that v, the y velocity, is 0. Substituting the time derivative of purple into the space derivative of orange gives us, where c equals the square root of gh, we have also assumed that the fluid is barotropic, which is it is well mixed and has a uniform temperature distribution. This is the non-dispersive wave equation of shallow waves. If we substitute the well-known harmonic solution into the purple equation, we obtain a solution of this form. Substituting these harmonic results into the grey equation results in whose solution is, recalling also that the Rossby radius is given by the square root of gh over the modulus of the Coriolis parameter, we arrive at a complete solution defined by x and y. The results of this Kelvin wave solution are as follows. Firstly, considering what happens at y equals plus minus infinity gives unrealistic values of eta, suggesting that such free motion cannot exist in the open ocean. Also, placing a rigid boundary at y equals 0, we notice that the only acceptable solution is that of the form minus kx. Note that there is also a decay of wave amplitude away from the coast. Finally, the exponential solution explains the existence of the horizontal pressure gradient displayed before. So next time you see Moana or Montanui staring at the edge of the water, just remember, it is a coastal Kelvin wave propagating along the coast with a Coriolis force acting towards the coast, balanced by a pressure gradient force acting away from the coast. And more physically, it is a gravity wave in a shallow rotating fluid.